The last two exercises in Chapter 2 look at the concept of three-dimensional trig. So we've been operating in 2 dimensions and 2 planes called the x and the y planes. And now we look at introducing a 3rd dimension. So it's actually a good idea to master being able to draw the concept of 3 planes. So you're quite familiar, I'm sure, with x and y, probably not drawn in this particular configuration, but we have an x-axis which is positive and a negative aspect, and at 90 degrees to that we've got a y-axis. Now what we're going to do is introduce our 3rd dimension, frequently called, or commonly called, z, and it goes up there and it goes then through down here. What you'll also see is maybe this called north, south and east or something like that. I'll just call it for now z. And what we know is that everything intersects, all these dimensions intersect at 90 degrees. Many of the questions lend themselves very nicely to this this 3-dimensional representation, because they're often talking about a tower or a tree or a building that is obviously coming up out of the ground. So that's 1 dimension from the ground up, and then on the ground we have 2 dimensions that meet at 90 degrees. Drawing the diagram, if it's not given, is one of the most difficult parts of these questions. There is no new trig, and really every calculation is based on either Pythagoras or right angle trigonometry. There may be a little bit of non-right angle triangle at times, but again, you know the sine rule and the cosine rule. So, labelling the diagram becomes an extremely important step. Understanding the diagram is also extremely important, because obviously if you don't get the dimensions in the right places on your diagram, the right values, then you're working with inaccurate information. And like I've said here, the questions become difficult because the diagram is complicated or difficult to visualise, or we're working with triangles without enough information to directly use Pythagoras and trig. So in that case, you might be required to form some equations and solve them. So, in general, draw a diagram. If it's not given, clearly label all vertices. And identify your right angles. So what you know is that the intersection of the planes is 90 degrees. Obviously anything, for example, located out here, standing vertical, also meets this dimension at 90 degrees. And note the shape of each triangle in the diagram. And really we're ideally trying to identify some right angle triangles. Let's have a look at the first example. So it says, from a point X, 25 metres due south of the base of a tower, the angle of elevation to the top of the tower is 47 degrees. Point Y is 15 metres due east of the tower. Draw a diagram containing this information and then find. So I think you will need to definitely read it 2 or 3 times. You can see that I've already indicated the tower as the 3rd dimension, and we can stay with our understanding of north, south, east and west. We'll draw them on a bit of an angle. I don't advise you to go north and south, east and west. It's too difficult then to show the third dimension coming out when you're on that angle. But if you just turn it slightly, so we go north, south, east and west, and then we can have the tower coming up as our third dimension. So just twist it slightly. So from a point X, 25 metres due south of the base of the tower. So we're here south of the tower and we're at the point X, and we know that's 25 metres. The angle of elevation to the top of the tower, so from here up to the top of the tower, is 47 degrees. And we know that from the tower out in this southerly direction would be right angle. So hopefully you can all see we've got a right angle triangle here. It's sitting up, coming out of the page with the right angle. The distance from X to the top of the tower is the hypotenuse. With respect to 47 degrees, this 25 would be adjacent, and the height of the tower would be the opposite side in the right angle triangle. Then talks about point Y is 15 metres due east of the tower. So we've got Y on the due east. Draw a diagram showing this information. So we've got that. And A says find the height H of the tower correct to 1 decimal place. Now, remember me saying that one of the difficulties, apart from getting a diagram right, is that you might have a triangle without enough information. But actually, I don't think that's going to be the case. The height of the tower correct to 1 decimal place. Here I've got a nice right angle triangle. The height is the unknown. This side of the triangle is 25, and we've got an angle of 47. You can see the two sides involved are opposite and adjacent, so that's tan, and we would have the tan of 47 is H on 25. And you can see then H is equal to 25 tan 47. Make sure your calculator is back in degrees, and it's given as 26.809, which is 26.8 to 1 dp. When you have a look at where theta is, it's nicely sitting in a right angle triangle. And I've just made sure I've done this, I hadn't previously, which was to make sure you've got all the information on your diagram. I hadn't actually initially put that 15 metres in, which would be problematic now when we move on to this question. So in this triangle that theta sits, the elevation from Y to the top of the tower, you can see that the height is the opposite side, 15 is the adjacent side. So we're going to use tan again, and also the height of the tower that we've just calculated in part A. So we set up our nice tan ratio, and we know that theta is tan inverse of that ratio, and using your calculator and the fraction button, you can see it comes in at 60.764 degrees, which we would round to 61 degrees. So really that was quite a straightforward example. And actually, since there are 2 more examples, I'm going to stop the video there and do each of these examples in separate videos.